Hi, today we study a new type of stoichiometry problem. One involving limiting reactants. And we will solve limiting reactant problems not using the bubble diagram, which we learned last week, but with the ice table. And I will tell you what the ice table is in this video. An example of a limiting reactant problem is this one right here. It is a stoichiometry problem. It starts off like almost all stoichiometry problems with a balanced chemical reaction. And so we're going to start off by copying that balanced chemical reaction. C13H10O5 plus 13O2 goes to 13CO2 plus 5H2O. You can see that this reaction is a combustion reaction. But just because the reaction is a combustion reaction doesn't make this a combustion analysis problem. Instead, as we will see, there will be a limiting reactant. Okay, so now in this problem, we take the combustion takes place in a piston with a chamber between, and now we get to the first line of the ice table, and the first beginning of the ice table is the I line. I stands for initial. And initially, we have 1.44 moles of C13H10O5. And it's very important in the ice table that we put moles. We don't put gram amounts into the ice table, only mole amounts. And we have, in addition to the 1.44 moles, we have 17 moles of O2, so that goes under the O2. And we have none of the products to start, so we put 0 here. And then the next sentence of the problem says, the reaction stops at only 80% of the maximum extent possible. And so what do I mean by maximum extent possible? Well, it's going to be the maximum change. So this is the C100, and this is the maximum extent change to the maximum extent. And to figure out what that means, we have to look at the balanced chemical reaction. The coefficient for C13H10O5 is 1. For every 1 mole of C13H10O5, I can run the reaction 1 mole reaction times. For every 1.44 moles, I can run the reaction more times. I can run it 1.44 mole reaction times. So mole reactions are the number of times you can run the reaction given that you have this much of the starting material. So we have a lot more of O2. We have 17 moles. But we can see that in the balanced chemical reaction, it takes 13 moles of O2 to run the reaction 1 mole reaction times. So if I have 17 moles, what I have to do is take the ratio, and this is 17 over 13 mole reaction times. I can run it a little bit more than 1 mole reaction times, because 17 is more than 13. If you do the math, this is 1.31 mole reactions. And now we get to the concept of limiting reactants. The C13H10O5 allows one to run the reaction 1.44 mole reaction times, but the O2 only allows you to run the reaction for 1.31 mole reaction times before you run out of compound, which makes the O2 in this case the limiting reactant. Okay, when we run this to the maximum extent possible, then we will use up all our O2. By the time we've used all O2, that's minus 17 moles of O2 have been used up, but we will not have used up all of the C13H10O5. Instead, for every 13 moles of this, we will only be able to use up 1 mole of C13H10O5, and if you do the math then, the amount of C13H10O5 that is used is minus 1.31 moles. Minus 1.31 is minus 17 divided by 13. If we use up 17 moles of O2, since the coefficient of CO2 is also 13, we make 17 moles of CO2. The ratio of H2O to O2 is 13 to 5, and therefore we take 17 and multiply by 5/13, and we get 6.54 moles. That's what would have happened if the reaction had gone to the maximum extent possible. But, as the problem says, the reaction stops at only 80%. So at 80%, this is C80, this is the change which actually took place. It's 80%, it will be the C100 numbers times 80%, and if you do the math, it's minus 1.05 moles, minus 13.6 moles, plus 13.6 moles, and plus 5.23 moles. Notice that in the C80 line, the ratio of the various numbers are in the 1 to 13 among the reactants and 13 to 5 among the product ratios. And finally, we get to the last line of the method, which is the end line. And the end line is the initial amount minus the actual change, the C80 line. 1.44 minus 1.05 is 0.39 moles. 17 minus 13.6 is 3.4 moles. We made 13.6 moles of CO2 and 5.23 moles of H2O. These are the final amounts. This is the answer then to the problem. We will practice the limiting reactant problem tomorrow in class.